Carbyne Stack, open source and cloud-native MPC. Hi, we are pleased to introduce Carbyne Stack, an open source cloud stack for building scalable, secure multi-party computation applications. Federated to serve. Carbyne Stack federates cloud instances into multi-party virtual clouds that provide distributed, decentralized services for storing and processing secret shared data. As Carbyne Stack implements a client-server MPC model, clients can consume these services to securely offload computation on sensitive data. With the current implementation, this allows any number of clients to collaborate securely on private data, where two Carbyne Stack instances act as the MPC parties. In the following, we refer to MPC parties as virtual cloud partners, VCPs, that jointly provide MPC services in a virtual cloud. Building blocks. Each VCP hosts an instance of the Custer, Amphora, and Ephemeral Foundation services, which provide data storage and processing functionalities. All services provide REST interfaces that can be accessed by the respective clients, which are also bundled within the Carbyne Stack command line interface. Custer. Custer stores offline tuples and serves them on request to Amphora and Ephemeral. Amphora. Amphora is the secret store that is used by clients to store and retrieve secrets. Amphora uses tuples from Custer to perform the secure up and download protocols when interfacing with clients. Ephemeral. Ephemeral is used to execute MPC programs using MP speeds. Any number of secrets can be fetched from Amphora at the beginning of an MPC program execution, and any number of secrets can be written to Amphora at the end. Ephemeral will fetch tuples from Custer consumed throughout the execution of the MPC program. Lifting MPC into the cloud. Underneath, Carbyne Stack builds on giants to lift secure multi-party computation into the cloud. So containerization orchestration is provided with Kubernetes, Knative to deploy MPC as serverless workloads, and Istio is used for flexible routing. Carbyne Stack can be deployed to any Kubernetes cluster on-premise and in the cloud. Demo: The Millionaire's Problem. In this demo, you will learn how to solve the millionaire's problem using an MPC function deployed on Carbyne Stack. To do so, we use a variation of Andrew Yao's millionaire's problem, that is the secure multi-party computation problem of deciding which of two millionaires, Alice and Bob, is richer without revealing their actual wealth. Since the conception of the problem, the world has moved on, and we better speak today not of two millionaires, but of two completely fictional billionaires called Jeff and Elon. As a prerequisite, we have deployed a Carbyne Stack virtual cloud backed by two virtual cloud partners locally. Each of the virtual cloud partners is deployed in an independent kind cluster and runs a private instance of all the required services such as Amphora, Custer, and Ephemeral. In addition, we used the Carbyne Stack command line interface configured to communicate with the VC. Before we can actually use the services provided by the VC, we have to upload cryptographic material. As generating offline material is a very time-consuming process, we provide pre-generated material which will then be consumed by the individual services. First, we define a unique identifier used to link related tuple shares across the virtual cloud partners. As of Carbyne Stack lingo, we upload tuples in bulks, so-called tuple chunks. Here, we will first upload a chunk of input masks, followed by a chunk of multiplication triples. We will upload the individual shares stored in separate files to the respective party. Then, we must activate the recently uploaded chunks on the individual cloud partners. With this, we verify that the related shares have been successfully uploaded to each of the partners and can now be consumed for sharing or computation. Now we can start with solving the millionaire's problem. To see how things work, let's put ourselves in Elon's shoes. First, we upload the inputs to our calculation into the Carbyne Stack Amphora secret store. The inputs are the billionaire's net worth in billions. Note that this obviously has to be done in a private way by Jeff and Elon in a real-world setting. Here, we use the CLI's Amphora create secret command to first secret share the given secrets locally, and then upload the individual shares to the virtual cloud partners. This command returns the unique identifier, a UID, used to reference the secret shares in Amphora. The ID is then assigned to the individual environment variables Jeff and Elon respectively. We can verify that the secrets have been created using the Amphora getSecret command, which will list the available secrets with their unique identifier and all tags associated to the given secret. Elon is eager to see whether he ranks first in the list of the richest people in the world. To check that using the Carbyne Stack platform, a well-known global media company which regularly publishes a list of the richest people in the world came up with the following MPC program that does the job. As the actual individual secret shares are stored in Amphora, the first and last section show boilerplate code which is required to allow Ephemeral to first receive the input shares and in the end write the individual shares of the program's result back to Amphora. What we can see is that the program expects two inputs and performs a single comparison between them. The result, written as a secret to Amphora at the end of the program, is either 1 in case the first input is less than the second, or 0 otherwise. Elon invokes the program using the ephemeral serverless compute service as follows. We pipe the just-defined program to the CLI's ephemeral execute command, which uploads the code with the additional parameters to the ephemeral services. Here, we define two input values referenced by the IDs stored in the environment variables Jeff's net worth ID and Elon's net worth ID, and trigger the computation on an ephemeral compute node called ephemeral generic.default. The code is then compiled online by the MP-Suite's runtime before both VCPs connect to each other using a dedicated discovery service to coordinate the execution of the program. The CLI spits out a list of identifiers of Amphora secrets generated by the programs. The snippet above extracts the single identifier emitted in this example and stores it in the result ID shell variable. Using this identifier, Elon can inspect the result of the execution using the CLI. The output being 0 tells Elon that unfortunately Jeff is the alpha. After buying a bunch of the fabulous new and completely fictional Carbyne Stack altcoin and posting a tweet that one of his companies will accept that coin for payments in the future, Elon wants to see whether he is finally in the pole position. He deletes his old and submits his new net worth and triggers the evaluation of the billionaire's problem logic again using the CLI. This time, the execution results in a 1, which creates a pleasantly warm feeling in Elon's chest. Demo. Benefit from cloud-native technologies. The last part of the demo has shown how to use Carbyne Stack in general. Now we will investigate how services can be scaled and new ephemeral containers can easily be deployed to suit specific needs. At first, we will deploy an additional ephemeral container which contains a pre-trained convolutional neural network for character recognition based on MP speeds. The model is trained on the MNIST dataset, which contains 70,000 images of handwritten digits. The images are grayscale and have a size of 28 to 28 pixels. First, we define a new Kubernetes service with a given configuration. This defines general parameters like ports to be exposed and, more important, the associated name and the Docker image to be deployed. Here, we have our customized ephemeral MNIST image, which has additional application dependencies installed compared to the generic ephemeral deployment and contains the trained MNIST image. The service configuration can be applied on the cloud partners using the Kubernetes CLI and be verified by the given command. Now we have to provide the input to perform the inference. This looks like an 8. Let's see what the neural network says about it. To do so, we have again to provide the secret shared input using Amphora. The first commands translate the image into an array of grayscale values from 0 to 255 for each of the pixels. You can inspect the uploaded object using the CLI. By using the ephemeral execute command with the respective arguments, we can execute the program. However, compared to the Millionaires demo, we will trigger the execution on the recently created ephemeral mnest.default node. What has also changed is that we do not provide program code with this execution, as the character recognition program is already part of the ephemeral container and must not be provided. Once the computation has terminated, we can fetch the result from Amphora using the CLI. As we can see, the MNEST program provides an array as a result containing the non-normalized predictions for each potential output of the inference, where in general, the largest value represents the most likely label. However, as Amphora is currently limited to unsigned integers as data type, the individual values must be converted from unsigned to signed integers first, and then to floating point numbers. The post-processing is done by a simple script. Therefore, we pipe the content of the inference result to that script and will receive the actual result of the inference. In order to compute probabilities and confidence of the predicted label, we are computing a softmax offline on the given result, since this computation is rather expensive from an MPC point of view, but must not be processed confidentially. The result shows that our image was classified indeed as the character 8 with a confidence of 99.98%. As a last quick demo, we will show how Carbyne Stack also profits from the cloud-native foundation services with respect to scaling and resilience. We can easily scale individual services like Amphora using the Kubernetes CLI. Listing the pods on our cluster will reveal that an additional Amphora instance has been deployed. This state will also be maintained even if we terminate one of the services manually. And Amphora is still up to normal. Current limitations. For the sake of transparency, we would like to list the current limitations of Carbyne Stack. Carbyne Stack is currently limited to a 2 virtual cloud partner setting, as the implementation of inter-VCP communication and service configurations are tailored to the 2-party setting. While the MPC online phase is performed by Ephemeral, tuple generation using an offline phase has not been implemented yet. In addition, streaming tuples from Custer to Amphora for program execution is not yet available. Ephemeral is therefore deployed with pre-generated tuples. Amphora does not differentiate data types and is limited to integers. Type conversion has to be done either within the MPC program or in pre- and post-processing steps. Carbyne Stack does not yet provide support for fine granular access management. Thank you for your interest and attention. If you are interested in Carbyne Stack and its feature roadmap, you can find further information on our website or our GitHub organization. If you have any further questions, please do not hesitate to contact us. Carbyne Stack, open source and cloud native MPC.